Hello intellectuals, I am SK Thakur and you are watching this video in Digital Maths Academy. So let's differentiate equation and identity. Let's you have a relation here x plus y equals to 8, right? So when you put the value of x as 6 and that of the value of y as 2, then we can see here 6 plus 2 equals to 8, right? So we can say 6 comma 2 satisfy the relation x plus y equals to 8. Similarly 7 comma 1, right, also satisfy the relation. Likewise we can say that 10 comma minus 2 also satisfy the relation. So there are so many values of x and y that satisfy the relation x plus y equals to 8. But when we put the value of x as 5 and that of the value of y as, we can say anything, right, that is 3, right? So 5 plus 3 equals to 8, But when the value of y equals to 4, right, then x plus y equals to 5 plus 4, that gives us 9, right? So we can say 5 comma 3 satisfy the relation, but 5 comma 4 doesn't satisfy the relation. So there are so many values of x and y that cannot satisfy the relation x plus y equals to 8, isn't it? So we can say x plus y equals to 8 is a relation which is true for certain values of x and y, isn't it? X plus y is not true for all the values of x and y. But in an identity, we see here a plus b whole square equals to a squared plus 2ab plus b squared, right? So it's true for all the values of a and b. For example, if a equals to 3 and b equals to, you can take negative also, doesn't matter. So here we can say a plus b, that is a plus b whole square equals to 3 minus 1 whole square, and 3 minus 1 means 2 whole square, and 2 whole square equals to 4. For the right hand side, we have a square plus 2ab plus b square, and for this a means 3 square plus 2 dot 3, b is minus 1, right? So we can write here minus 1 and plus minus 1 whole square, and here 3 square is 9, and 2 3 the 6 into minus 1 is minus 6, and square of negative is always positive, so we can write here plus 1. So 9 plus 1 is 10 minus 4, 10 minus 6 equals to 4, right? So left hand side is also 4, right hand side is also 4, right? So it's true for a equals to 3 and b equals to minus 1. We can check the identity by so many values, and it's true for all the values of a and b, right? So there are so many identities. For example, here a plus b whole cube also, right? That is a cube plus 3a squared b plus 3ab squared plus b cube, right? So we can check this identity by so many values of a and b also. Please check by some values and please write whether it is true for all the values of a and b, for a and b or not, and write your conclusion in the comment box. Another identity we can select as a squared minus b squared equals to, we can say that a plus b equals into a minus b, right? So it's also true for all the values of a and b. Just we select the value of a as 7 and that of b equals to 4. Yes, we can select any value, doesn't matter. So we can write here a squared minus b squared equals to 7 squared minus 4 squared, right? And 7 squared equals to 49 minus 4 square is equal to 16. So this becomes equal to 33, right? Right hand side we have here a plus b into a minus b, right? So we can say here a plus b equals to, there's a 7 plus 4, and a minus b, that is 7 minus 4, and that is 11 into 3, that also gives us 33, isn't it? So left hand side equals to right hand side. So such type of relations are true for all the values of a and b. In some identity, for example, we have here sec square a minus tan square a, that equals to 1. Okay, so if you put the value of a, at any angle, right? For example, 0 degree, 30 degree, for example, let's we put the value of a as 30 degrees, so we can write here sec square 30 degree minus tan square 30 degree, right? That's the left hand side. So we have here sec square 30 degree. We are going to find out its value, sec square 30 degree. So sec square 30 degree means sec 30 degree. Actually we have here root 3 by 2. Actually sec 30 degree means just reverse of cos, so we can write here 2 by root 3, right? 2 by root 3 its whole square, and tan 30 degree means 1 by root 3, so we can write its whole square, right? So when we simplify them, that becomes 4 by 3 minus 1 by 3, and 3 is LCM, so we can get here 4 minus 1, that is 3 by 3, right? And 3 by 3 equals to 1, isn't it? So right hand side and left hand side equals to 1, you know. So such type of relations are true for all the values, but we can see in this identity there are trigonometric ratios. So the identity in which there are trigonometric ratios are known as trigonometric identities, right? Identity is a relation which is true for all the values, but equation is the relation which is true for certain values. Here we have some points that are used to prove identities, right? So first of all, we have to choose the complex side, so we have to see clearly, you know, in which side there is complex, so we have to choose that side only. Another one is basic trigonometric formulae are proved by previous relation. For example, if we have to prove that sine squared a plus cos squared a equals to 1, right? It's an identity, so we can prove it by sine squared a means we can write here b squared by h squared, right? And cos squared a means b squared by h squared, right? And that gives, when we take h squared as LCM, so we have here p squared plus b squared, and according to the Pythagoras theorem, p squared plus b squared is equals to h squared, and h squared by h squared equals to 1. So this identity, such type of identities are proved by the help of previous relation. Another one is basic trigonometric formulae, right, are directly applied. For example, if we have cos a into sec a, right, so we can directly write equals to 1. Next one is basically the trigonometric ratios are changed into sin and cos. So during the solution, sometimes we see there are tan, right, there are cosec, okay, there are sec, okay. So such type of basic relations are, such a basic trigonometric ratios are, you know, are changed into sin and cos. For example, tan equals to sin by cos, cos equals to 1 by sin, right, sec equals to 1 by cos, and so on. Here we have the first identity. To prove it, we are going to select the left hand side, because left hand side is only complex here. So left hand side is cos alpha dot cosec alpha dot tan alpha, right, over here is sin alpha dot sec alpha dot cot alpha. So now we write cos alpha as it is, and cosec alpha we can write here 1 by sin alpha, because sin and cosec are reversed to each other. Tan alpha we can write sin alpha over cos alpha, and at the denominator sin alpha as it is, sec alpha we can write 1 by cos alpha, and cot alpha we can write cos alpha by sin alpha. Now we can cut cos alpha to cos alpha, sin alpha to sin alpha. Here also sin alpha, cos alpha, yes, we can sin, cos we can cut. Now we can see at the numerator we have 1, and at the denominator also we have 1, and 1 by 1 equals to 1, which is equal to the right hand side, right? And then at last we can write here proved. Identity number 2. So we are going to select left hand side here also. So we have cot square a dot sec a over cos square a dot sin square a, right? So we can write cos square a equals to cos square a by sin square a, because this is a formula, and sec a equals to 1 by cos a. At the denominator, cos square a and sin square a we can write as it is, right? After that we can write here cos square a into 1 means cos square a only, and at the denominator we can write here sin square a dot cos a. and at the denominator here we have cos square a dot sin square a. Now as we know, a by b by c, and if the down one is the main line, so we can write here a by bc. And if we have here a by b by c, and if the upper one is the main line, we can write ac by b. So applying this concept, we can write here cos square a, and at the denominator we can write here sin square a dot cos square a dot sin square a. Of course, yes, we can write. After that, cos square a, yes, we can cut. Yes, here cos square a, that we can cut now. And after that, at the numerator we have only 1, and at the denominator here is cos a, we can write, and sin square a dot sin square a gives us sin to the power 4a, and 1 by cos a we can write here sec a, and 1 by sin to the power 4a we can write cosec to the power 4a. That's our right hand side, so equals to right hand side, of course you can write, and then at last we can write here proved. Number 3, let's select left hand side here also. So left hand side equals to sin theta divided by sec theta divided by cos theta divided by sin theta. So here sin theta divided by sec theta, so we can write here sin theta by sec theta. After that, here is division sign, and we can write here cos theta by sin theta. Of course we can write. Now sin theta, here we have sec theta, so we can write sin theta over 1 by cos theta, because sec theta equals to 1 by cos theta, and there is a division cos theta by sin theta. After that, here we have the main line. Okay, upper one is the main line, so here it becomes sin theta dot cos theta by 1, and here division sign changes into multiplication, and due to which we can write sin theta at the numerator and cos theta at the denominator. Now we can cut cos and cos very easily. Then we have here sin theta dot sin theta equals to sin square theta, which is at our right hand side, so we can write here proved. So number 4, let's select left hand side. So left hand side equals to cosec to the power 4 alpha minus cosec square alpha, right? So we are going to take cosec square alpha as common, so inside the bracket we will have here cosec square alpha minus 1, right? Now cosec square alpha means 1 plus cot square alpha. Yes, it's a formula. And cosec square alpha minus 1, it's equal to cot square alpha, because we know it is a relation cosec square a minus cot square a equals to 1. So from this relation, cosec square a equals to 1 plus cot square a, right? And cosec square a minus 1 equals to cot square a. And when you open the bracket, we can write here cot square alpha plus cot to the power 4 alpha. And according to the right hand side, we are going to arrange it, that is cot 4 alpha plus cot square alpha, right? And that's equal to the right hand side. So we can write here at last proved. Number 5, left hand side equals to tan square a minus sin square a. So we are going to change tan square a into sin square a by cos square a, and then we have here sin square a also, right? After that, we are going to take sin square a common. Of course we can take common, so we have here 1 by cos square a minus 1, and then we can write here sin square a, and 1 by cos square a means sec square a minus 1, and then you can write here sin square a, and sec square a minus 1 equals to tan square a. Now according to the right hand side, we are going to arrange it, so tan square a into sin square a, that's equals to the right hand side, and we can write here proved. Very soon I will come up with a new video of second case of trigonometric identity. Kindly not to forget to like, subscribe and share my video. Thank you. Have a nice time.